Today we're going to briefly look at the distribution function for a hypergeometric probability function. And first of all, the distribution initially was derived in a publication by de Moivre in 1711. And what the hypergeometric distribution is the distribution of the number of successes when we are sampling without replacement from a finite population, each of whose members could be classified as either success or failure. Now again, the success failure here may not have its usual connotation. It's just simply a categorization of the event. So what I have here is capital N, which is the population size, and suppose from the population we choose a sample of size little n. We're going to let capital K be the number of successes in the population, and little x is the number of successes in the sample. So that means capital N minus capital K therefore should be the number of failures in the population, and likewise little n minus x would be the number of failures in the sample. So what is the sample space for x before we actually write the distribution function here? So in order to come up with the sample space for x, we can make the following observation. The number of successes in the sample could be at most as large as the sample size, right? So we're going to write that. And also, the number of successes could be no more than successes in the population, right? So for example, let's say the population has only 5 successes and our sample is size 100. So it cannot exceed, the number of successes in the sample cannot exceed 5, which is the maximum success in the population. So therefore we have the intersection of these two sets. So from this we can quickly arrive at a what I call an upper bound for the number of successes in the sample should be therefore the minimum of the sample size or number of successes in the population. Okay. Now what about the number of failures? Well, the number of failures in the sample again could be no more than maximum, the sample size, and also the number of failures in the sample cannot exceed the number of failures in the population. All right, and from this we actually get an expression that looks like so. So the number of failures in the sample should be equal to the minimum of the sample size, or n minus k, capital N minus k, just like the one above it. Okay, now in this expression, if I multiply both sides by negative, okay, so I'm multiplying both sides of this expression by negative, then this becomes x minus n. I'm going to change the direction of inequality, and we can write this. The minimum now becomes, the way the negative works in this, the max of negative n, or k minus n. Okay, now if I add n to both sides of this inequality, okay, so then equivalent expression would be x is equal to the max of, and the way adding n to both sides here works is that negative n and n makes 0, and then we have k minus capital N plus n. Okay, and this will give me a lower bound for the number of successes in the sample. Now having both of these, we can actually now write the distribution function. So probability random variable x takes on a specific value of x is given by, in function notation, that would be f of x with the parameters little n, capital K, and capital N. And the form of the distribution function is therefore given by k choose x. That's how many ways we can choose number of successes from successes in the population, and the remaining number of items in the sample should be failures, and that's how many ways you can choose little n minus x failures from capital N minus k in the population. And of course, the denominator is the sample space, which is all possible samples of size little n from population capital N, each of which is equally likely to draw. Now, the parameters of this distribution function. Well, the population is a count, so it's going to be a positive integer, right? That's the population size. The number of successes in the population could be at most the population size, or lowest it can be is 0, cannot be negative. The sample size has to be at least 1, right, up to the population size. And finally, we're going to attach the parameter space for x in here also. So I'm just going to put the lower bound, which is maximum of 0 or k negative n plus n, and greater than or equal to x, and less than or equal to the minimum of n and k. Okay, and that is what, again, the restriction on the sample space for x is. Now, the name, by the way, is derived from the corresponding function in the field of analysis. So, I just wanted to briefly clarify how we come up with, again, the parameter space for, this is the thrust of what I wanted to do. How do we come up with the parameter space for x in a hypergeometric distribution? For a more detailed treatment of the hypergeometric distribution function, as well as how to find the mean and variance of this distribution, I have a link in my YouTube under description, so you can use that in order to find out more about this distribution. And we are done with this presentation.